So it's now I object actually to the joke. It was a joke. It's one of these engineer, physicist, mathematician jokes that glorifies the wrong group. Anyway, so the joke is, if there's a fire in the room, a bucket of water, an engineer takes the bucket of water, pours it on the fire, puts it out. Physicist just sort of elegantly sprinkles the water around the fire, and the fire works out the rest for itself. And a mathematician just convinces himself that there's a solution and leaves. Quite a good joke. As I say, the wrong group comes out best in that joke, but that's okay. Okay, so I felt bad, Yeah. So what happened yesterday? Yesterday I was going to do the Unruh effect, and I was going to do it the not slick way. We were just going to do it the kind of cut and dried way where it was going to work out great, and you were going to really believe me about the answer. And then I tried to work it out the morning of the lecture and found that actually there's an integral that's too gross to do in lecture. So I left you without an actual punchline. So I just want to correct that and actually do it the slick way, because the slick way is also very important. Very important trick to know, and then it'll lead us into the cosmological case. So yeah, we want to redo the Unruh effect, and then see how with the slick way you get the same. You can also calculate the Hawking effect, evaporation of from black holes, and the temperature of de Sitter space. And then, if inflation is right, the temperature in de Sitter space is actually this is the first, this is the one case of quantum field theory and curved spacetime where we already have observed in detail the results. These are exactly the fluctuations in the cosmic microwave background. So anyway, we want to unpack those statements. But so for starters, let's just say a word about. So the slick way relies on this notion that a thermal state is, in some sense, periodic in imaginary time. And that by finding the period in the imaginary time direction, you can infer the temperature of the state. So, okay, so what does that mean? I want to say it's not so mysterious as it sounds, but anyway, maybe it is very mysterious. I don't know. I think it's what I mean to say is the algebra is very simple, and the reason the trick works algebraically is pretty clear. On the other hand, it may also be something very mysterious. There may well be something deep and thermodynamic going on with gravity. Okay, but so what's the story? So if you have in quantum mechanics, if you have a state psi1 at time t1, and you have a state psi2 at time t2, then you want to calculate the amplitude for what is the amplitude that psi1 at t1 will evolve into psi2 at t2. You use the time evolution operator, e to the minus iht, the quantum mechanical time evolution operator. You just take state psi1, you evolve it for the relevant amount of time, minus ih t2 minus t1, and then you project it onto the state of interest. Okay, so that's quantum mechanics. Then in statistical mechanics, in quantum statistical mechanics, a thermal state, you can always go in quantum mechanics. You can always take a pure state and just rewrite it as a density matrix. And then every quantity you would have calculated in the ordinary way, you can recalculate with the density matrix. So for example, the expectation value of any operator A, you now calculate in the density matrix formalism by calculating the trace of rho A. Okay, but this formalism is more general because it can now accommodate not just density matrices that are pure states like this, that can be represented as the outer product of a single state with itself, but things that are arbitrary, not arbitrary, but things that are sums of such states, classical probabilistic distributions over such states. And in particular, the state that represents thermal equilibrium in quantum statistical mechanics is the state that is, so the thermal state, rho sub beta, I'll call it. I'm going to be using this notation, beta is equal to 1 over the Boltzmann constant times T graph. So beta is just 1 over time. 1 over temperature, I mean. So yeah, the density matrix here is e to the minus beta h. So in other words, this is a sum of all the energy eigenstates of the system, incoherent sum of them, each weighted by a factor of e to the minus e over kt, the Boltzmann factor associated with that state. Okay, so now if we, the basic thing we calculate in quantum statistical mechanics is the partition function, which is just the trace of rho. Which, in other words, let's write that out a little bit more explicitly. That's just the sum over some complete orthonormal set of states psi m of psi m e to the minus beta h psi m. And similarly, and again, similarly, if we want to calculate any expectation value of any operator or string of operators, we will just take the trace of it with our density matrix. Okay, so now the key thing is that when we're calculating, so let's just look at a single term in this sum, a single term in one of these traces. So just look at this guy. So if we compare this expression with this expression, we said, well, this is the amplitude for a state at time for state psi 1 at some initial time to go to a state psi 2 at some later time at some time delta t later. Let's call this thing delta t. So this is just identical to that, but it now says it looks formally identical to that if we write if we just identify minus I delta t with minus beta, or in other words, if we just identify delta t with minus I beta. Okay, so in other words, somehow what this thing is saying, this is just formally speaking exactly the same as saying calculating this amplitude is calculating the amplitude that if we start at some state psi m and then evolve it in the imaginary time direction, whatever that means, by some what it means is we just use the equations, but we follow them in the imaginary time direction from the initial time instead of in the real time direction. We follow them in the imaginary time direction by an amount minus I beta. What is the amplitude that the state will come back to itself? Okay. So you begin to see the point here that the state is coming back to itself after an evolution by this amount in the imaginary time direction. Just to make things a little bit more explicit, the point is that this was Dirac's original way of evaluating a quantum amplitude, but then Feynman came along and this is the canonical approach to quantum mechanics. But then there's the path integral approach due to Feynman, which again secretly is due to Dirac. Or in any case, due to some combination of the two of them, originally suggested by Dirac. Yeah, you know what you do here is you take the path integral over all field configurations that interpolate between this initial state psi1 at time t1 and this final state psi2 at time t2. You integrate e to the I action over all such interpolating configurations. And so exactly the same thing can be done here. That you can evaluate this thing with a path integral. But now what we're talking about is you take the path integral over all possible configurations in configuration space. But now the only configurations of interest are the ones that interpolate between the state psi m at time t and the exact same configuration at time t minus I beta. So in other words, to evaluate in statistical mechanics, you're doing path integrals just like you do in quantum mechanics, but the paths are always periodic with the same periodicity in the imaginary time direction. And that periodicity is nothing but, 1 over that periodicity is nothing but the temperature of the thermal path integral you're doing. Okay, so then Hawking and Hawking and who? Hawking and Hartle, I guess. Maybe I think maybe just originally Hawking. I don't know. One of Hawking and some maybe also Hartle. Had the bright idea that you could. So first Hawking had just calculated using the traditional canonical approach. This sort of approach using the creation and annihilation operators and calculating the Bogoliubov transformation, the Bogoliubov coefficient beta that we were focused on in the previous lecture. He just calculated that beta squared for a black hole was a thermal distribution. And then they realized that they could redo that calculation much more simply. Much simpler calculation could be done to recalculate the same effect, the temperature, the fact that the black hole emits a thermal spectrum, and what the temperature is. And they could do it using this path integral idea by just taking the metric and rotating the time direction to the Euclidean direction, and seeing that, aha, the metric actually does have a natural periodicity in that direction. And from that periodicity, you can read off the temperature. So you can do the same trick for the Unruh effect. So let's just do that quickly, and then look at the cosmological case. The Unruh effect really is the simplest case in that regard. So in the Unruh effect, we start with, again, we'll just look at the two-dimensional metric minus dt squared plus dx squared. And now let's make basically the coordinate transformation that I described more elaborately yesterday in a bunch of steps. But to save time, let's just cut to the chase here. So let's make the coordinate transformation t is equal to rho sinh sigma, and x is equal to rho cosh sigma. Okay, so rho is going to be the new spatial coordinate. Sigma is going to be the new time coordinate. And if we draw the picture here, if these are the Cartesian coordinates on Minkowski space, x and t, and this is the light cone, then in these new coordinates, I'm drawing curves of constant rho here, and then lines of constant sigma are like this. Okay, so this is what marching in time means. This is what marching in space means in this metric. So if we do the coordinate transformation here, we just take the differentials of these two expressions and plug them in here. We get basically this term becomes this term, and this term becomes this term. Okay, so we get a metric that looks like this. So this is the time-like direction, and this is the space-like direction. And I've just written it this way because now what we want to do, our next step is where we're supposed to look at what this metric looks like in the. Let's just ask ourselves what this metric looks like if time runs in the imaginary direction. So let's just define sigma is equal to I phi, and let phi be the coordinate that runs along the real axis, so that sigma runs along the imaginary axis. Okay, then now this this becomes this metric, but that is literally exactly the Minkowski. That is literally exactly the Euclidean metric, dx squared plus dy squared, two-dimensional Euclidean metric. If we make the coordinate transformation, that the usual change to polar coordinates, x equals cosine phi times rho, and y is equal to sine phi times rho. Okay, if you just take the Euclidean metric, change to polar coordinates, you'll get exactly this metric. Okay, so really we are just we have a periodic metric staring us in the face. The coordinate theta, the coordinate phi, is periodic with periodicity 2 pi. And so now remember. But now if you look back here, the proper time. So if we look at an accelerating observer is one of these guys riding along a curve of constant rho. So let's say that constant is rho naught. So if we look at the curve characterized by a constant rho naught, so now this is just a constant in front here. So we take a little step in d sigma here. The amount of proper time that has elapsed is rho naught times d sigma. In other words, if we for a time-like observer, ds squared is just minus their proper time squared. So if for fixed rho we make a march in d sigma, d tau is just equal to rho naught d sigma. Tau is equal to rho naught sigma. So if sigma has periodicity 2 pi, tau has periodicity 2 pi rho naught. And so we would say such an observer sees themselves in a thermal state with temperature, so beta, periodicity here. This is the periodicity in the imaginary direction. That's to be compared with beta. So beta is equal to 2 pi rho naught. Now, it happens to be the case. We haven't worked this out, but if you just calculate the 4 acceleration, so you take one time derivative to get the 4 velocity, take a second derivative along the motion to get the 4 acceleration. This guy has a constant 4 acceleration given by 1 over rho naught. So this is really the temperature that observer sees is 2 pi. Sorry, the beta that observer sees is 2 pi over his acceleration. But beta is nothing but 1 over the temperature. So in other words, the temperature is equal to the temperature you see in empty space is your acceleration divided by 2 pi. Okay, so that's a lot easier way to derive the result. It's just that it's a little bit too slick. Like if no one had derived it the nuts and bolts way first, and similarly for the black hole, then no one would have believed this calculation probably. But I wouldn't have believed it. I mean, nutty calculations like this are done all the time. Most things at that level of rigor, are wrong. Especially if they're the first calculation of their kind. Okay, so anyway, that in short is the idea.
So was it Gary Gibbons? This talking?
Oh yeah, maybe it was Gary Gibbons. Thanks. Actually, I'm not even. Well, anyway, definitely the 3 of them were during that time writing a lot of great papers on more or less this area. I think you are right that it was Gary Gibbons who was on the first paper with this approach. Okay, so let's do de Sitter space now. So and we'll just be quick about it. I think in Ruth's class I heard that you did a similar calculation for the Schwarzschild metric. Anyway, so I'll try to be brief about this, but do enough of it that if you were not in Ruth's class, you'll still follow it. But remember the Schwarzschild metric would be this, right? The Schwarzschild metric would be 1 minus 2m over r dt squared plus 1 minus 2m over r all to the minus 1 dr squared plus r squared times the metric for the 2-sphere. That's the Schwarzschild metric in standard Schwarzschild coordinates. So that the de Sitter metric has so-called static coordinates in which the metric looks almost identical to this. The only thing is that 2m over r is replaced by r squared over the de Sitter radius squared. Okay, what's going on here? Remember the way we constructed de Sitter space, this is 4-dimensional de Sitter space. We started off with 5-dimensional Minkowski space, we started off with 5-dimensional Minkowski space with these light cones. And then de Sitter space we constructed as a hyperboloid of radius of curvature rho naught, hugging the light cone. So our original coordinates were we had n plus 1 of them. Well, let's say we had 4 plus 1 of them. And anyway, the coordinate transformation you can do to get to static coordinates. Oh, well, I'll put it in the lecture notes. It's not crucial that I say it right now. There's some simple coordinate transformation you can go from that if you just plug it into the metric we derived in the previous lecture, will take you to this metric. So anyway, these are the static coordinates because none of the coefficients has any time dependence, right? Just like in the Schwarzschild metric. Okay, but now the picture in the Schwarzschild metric is that these coordinates apply from the radius of the black hole, from the horizon of the black hole out to infinity. So r runs from 2m out to infinity. And when you get to the horizon, these coordinates really break down. You have to switch coordinates to go smoothly through. We live out here, outside the horizon, and this is some surface beyond which we can't receive signals. So if we get too close, we fall in, and if someone inside tries to send us a signal, they are dumb. But the de Sitter space is like this. They are, anyway. They're not, we won't get their signal. It's too strong. They're probably desperate, first of all. Who wants me to go on with this? Nobody. Okay, I'll do it. So in de Sitter space, the situation is this. These coordinates apply for r running from 0 up to the de Sitter radius rho naught, at which point they break down. And so again, if your friend gets too close to the de Sitter radius, then they're going to have a very strong rocket to not get pulled out of the de Sitter radius. And once your friend gets pulled out of the de Sitter radius, then if they try to send you a signal, they're in the same situation as the poor guy in here who tried to send you a signal, except this person will die a gruesome death in a singularity, and this person you'll just lose him as a friend. Okay, so anyway, so what we want to do is look, with these curved spaces, just like in the Schwarzschild case, if you did it, the whole metric is obviously not equivalent to the Unruh metric. It's not equivalent to the Rindler metric, and the Euclidean version is not equivalent to the metric for Euclidean, ordinary flat Euclidean space, because these are curved metrics. Like, we shouldn't expect to get some global agreement between these two guys. Instead, what happens is that if you zoom close to the horizon, if you look close to the horizon, then the two metrics are equivalent. And so you probably did some coordinate transformation that let you zoom in on the horizon here. And let's just do it in this case, because that's the actual situation that we want to study. So I won't redo the Schwarzschild case, but it's exactly analogous to what I'll do here. So let's look at radii close to the boundary here. So let's look at radii that are almost at R0, but minus a tiny bit, capital R. Okay, so in other words, I'll change new coordinates, capital R. So if I do that, the expression 1 minus R squared over rho naught squared becomes 1 minus rho naught minus R, where this is a lot smaller than this, squared over rho naught squared. So if I expand this thing in parentheses here, the first thing I'll get is a rho naught squared over rho naught squared. So I'll get a minus 1, which cancels that 1. So that dies. And then the next leading term is the one that I want to focus on. The next one is where I get a minus 2 rho naught times capital R over rho naught squared. So this whole thing becomes 2 R over rho naught, approximately. And so the metric over there becomes, the de Sitter metric becomes, or the line element, I should say, becomes minus 2 R over rho naught dt squared plus 1 over 2R rho naught dr squared, and then plus the angular part, which I'll ignore. Why did I get a different? Okay, yeah. I think this is right, and I made an error in my notes. Basically, we want to make this now. This metric now really is equivalent to this metric when we go to imaginary time, or it really is equivalent to this metric, and we want to just make the final coordinate transformation to see that. So let's just convert this term so that it becomes the d rho squared term. So just to not confuse things, since we've already used rho here, I'm going to call this d chi. Okay, I want to change that to d chi squared. So that means that d chi is equal to the square root of this, dr times rho naught and so when I integrate this, I find that chi is equal to, I think I find that it's equal to 2 rho naught, square root of 2 rho naught, r to the 1/2. Who's with me? I could be making algebra errors because I made an algebra error here. Now I'm just going by the seat of my pants. But anyway, I think that's right. So now if we just take that and plug it in over here, I guess this guy becomes chi squared over rho naught squared dt squared, and then this guy becomes d chi squared, and then plus the rest of the metric. And so what you see is that this metric looks exactly like this metric, where d sigma up there is equal to what we used to call d sigma is now dt over the constant rho naught. Other than that, the two metrics are identical. What we used to call rho, we now call sigma. What we now call chi. Okay, but the bottom line is that just as we found that sigma in Euclidean space had period 2 pi, it just became the angular coordinate and polar coordinates. This has period 2 pi, so t has period rho naught times 2 pi. So beta, again, the temperature of de Sitter space, beta, 1 over the temperature of de Sitter space, beta, is 2 pi times the de Sitter radius, or in other words, the temperature. So now, the de Sitter radius is nothing but 1 over the de Sitter Hubble expansion rate. We'll see shortly. So this is really saying, just like the UNRRA expression was that beta was 2 pi over the acceleration. Beta in the de Sitter case is almost exactly the same. It's 2 pi over the Hubble rate. And so the temperature, in other words, is the Hubble rate of de Sitter space over 2 pi. Okay? You know, I blew my joke right at the beginning of the lecture. On the other hand, I feel it is time for a joke. So a brick is laying on the beach. You know, it's relaxing in the sun on the beach, and a bunch of geese fly overhead. They're flying south for the winter, and they say, "Hey, brick, you know, come fly south with us. We're going to where, you know, it's going to be warm all winter." But the brick just doesn't. He just keeps laying there. Some people are like that. Anyway, okay. Never ceases to amaze me that you guys laugh sometimes at these things. Anyway, okay, but it's good. It's good. It's I mean, okay. So now that's maybe all I wanted to say about. In other words, let's get to cosmology now. So why did we calculate the thermal effect in de Sitter space? Well, so before we do the calculation more correctly tomorrow, I just wanted to give a sort of simple physical picture of what's going on in de Sitter space. So, you know, in general, a very important thing to keep in mind. So, like, what are the three most important things to keep in mind in cosmology? Any cosmological problem will fall to you if you just have three initial thoughts when confronted with it. Okay, so the universe expands and contracts some way, and it's easy to solve. Or it expands, let's say, it undergoes some expansion history. And as it expands, or contracts, or whatever it does, the temperature evolves accordingly, and the density dilutes accordingly, and so on. You know, some of the key things that we want to pay attention to are that, you know, as the universe evolves, if you have, first of all, there's a distinction between how relativistic particles behave and how non-relativistic particles behave. And then there is a distinction between whether some particles are in thermal equilibrium with the rest of the matter in the universe. So is thermal equilibrium valid for a given particle, or, you know, which particles have fallen out of equilibrium? Okay, so you want to sort of distinguish in your mind between which are the relativistic particles and the non-relativistic particles at a given time, which particles are in thermal equilibrium and which ones are not. Now these two we said are very closely related. Often the way something falls out of thermal equilibrium is that if it has some mass, then as the temperature drops below its mass, so that it suddenly transitions from relativistic to non-relativistic, thermodynamics wants to eat it up and get rid of it, suppress its abundance by the Boltzmann factor. So it becomes exponentially rare very quickly as the universe expands past that point. And soon it becomes so rare that it just can't maintain thermal contact with anything else. Okay, so now I just want to add one more thing to that, which is that, so the universe is not really homogeneous. It has perturbations in it. And those perturbations are arguably the most important thing about it. They're the thing that we get that gives rise to interesting behavior and all the interesting behavior, and they're also the main thing that we can observe about the universe. Okay, so again, there's just one crucial thing to keep in mind when thinking about perturbations, which is just, so the universe is some big mess, right? I mean, when it's not homogeneous, then any quantity you're interested in, let's say the density, is some oscillating function, some disgusting function, random function of space at a given time. But don't think about the whole thing. Always Fourier decompose into spatial Fourier modes in cosmology. So break this guy up, break up this arbitrary function of space into its Fourier components. Because the fact that the universe is, to a first approximation, translationally invariant in space, that means that at linear order, as long as these perturbations are small, so that they're quadratic, so that their nonlinear interactions with one another are negligible, which is true for much of the universe much of the time. I mean, it's an observational fact about our universe that that's true for much of the universe much of the time. Then symmetry prohibits these guys from talking to one another. And so each Fourier mode just evolves independently. And you can just think about the evolution of, you can just focus on a single beautiful sine wave, which in co-moving coordinates has a fixed wavelength. Okay? So, and now all you have to do is think about how does its amplitude evolve in time. So if what I'm plotting here, so in other words, remember, as the universe expands, the distance between, the physical distance between two galaxies grows proportional to A. Physical distances grow proportional to A. But co-moving distances, the distances labeled by the co-moving spatial coordinates, the coordinates that I draw with a marker on the surface of my balloon that's inflating as the universe expands, those distances don't change. So you just factor out, it's very convenient to factor out the expansion of the universe and work in co-moving spatial coordinates. So let's say I'm plotting co-moving distance on the board here. So I focus on one particular Fourier mode of the density field, let's say, at early times. And then as the universe evolves, it doesn't stretch. Physically, its physical wavelength stretches proportional to A. But its co-moving wavelength stays constant. And my only job is to figure out what is its amplitude. The only thing I need to figure out is what does its amplitude do as a function of time? Does it oscillate up and down with a fixed amplitude as the universe evolves? Or does it stay totally fixed, not oscillate at all? Or does it oscillate up and down, but with a rapidly decaying amplitude until the mode has essentially disappeared? That's my job. That's my job when I'm trying to understand how the perturbations in the universe evolve, how any of the interesting stuff in the universe evolves. And so here, the crucial, most important thing is just to check: is this co-moving wavelength? It's fixed in co-moving coordinates, but it is growing in physical scale. Okay. So A times lambda co-moving is the physical wavelength of this mode. So it's changing as a function of time. And then there's this other important scale in cosmology, a natural length scale associated with the expansion of the universe itself, which we've met before, which is 1 over the Hubble expansion rate. Really, c over the Hubble expansion rate. We'll have units of length, but anyway, I'm going to set c to 1. And so this is the Hubble length, the physical Hubble length. You just want to compare which of these is bigger. Okay, there's going to be a dramatic transition whenever these guys cross each other. Usually, the situation will be, when you solve the equations, that if lambda is bigger than the Hubble radius during any epoch of the universe where that's the case, its amplitude is just fixed. So if it's initially perturbed in the early universe and it was longer than the Hubble radius at that time, it just waits around, frozen like this, until the Hubble radius catches up to and surpasses it. And then it begins to oscillate. So if this is a primordial gravitational wave, that was much longer than the Hubble radius at the beginning of the radiation epoch, the beginning of the radiation-dominated epoch, it just sits there with a fixed amplitude, and then once the Hubble radius gets longer than it, it begins to decay away rapidly. So by the present time, it's a very weak gravitational wave. On the other hand, if this is a primordial density perturbation, at the beginning of the radiation epoch, when it was longer than the Hubble radius, it just sits there. So if its initial amplitude was 10 to the minus 5, if the peak here was 10 to the minus 5 greater than the average density of the universe, and then the trough was 10 to the minus 5 less than the average density of the universe, it just sits there until the Hubble radius catches up to it. And then, after the Hubble radius catches up to it, it doesn't oscillate, it begins to grow. And it grows until it turns into a galaxy or cluster of galaxies, a dark matter halo. Okay, so that's the key thing. And so what I was just describing was the late universe. During the radiation, ever since the beginning of the radiation-dominated epoch, in our plot of the standard model of cosmology. So there's the radiation-dominated phase and the matter-dominated phase, and then recently the dark energy-dominated phase. And we live here. And again, I'm plotting log of the scale vectors of the universe is expanding in this direction. And here I'm just plotting the log of the densities of the various components. So ever since the universe has been doing this, it has been decelerating. Okay, neglecting the fact that it's beginning to accelerate now, but for all intents and purposes, ever since the radiation-dominated epoch, which began some microscopic fraction of a second after the Big Bang, the universe has been decelerating. During the time that it's decelerating, the Hubble radius is growing faster than the physical wavelengths, which are proportional to A. So 1 over h is growing faster than A when the universe decelerates. So we're in the situation that I just described, where modes in that epoch were initially that were initially longer than the Hubble radius. If they waited around long enough, the Hubble radius would eventually catch up. So, the idea of inflation is the opposite. That it posits that there was an epoch prior to the radiation-dominated epoch, during which the universe was accelerating. Okay, so when the universe is decelerating, the Hubble radius grows faster. But when the universe is accelerating, the Hubble radius, well, it turns out the Hubble radius, we'll see, stays, if the universe accelerates with W approximately equal to -1, in other words, if it's basically driven by something that looks and acts like a vacuum energy or a cosmological constant, in other words, where its pressure is equal to minus its energy density, then actually during inflation, this thing will stay constant. And in de Sitter space, de Sitter space is the case where literally the only matter density is strict vacuum energy, strict positive cosmological constant. In that limit, RH is really a constant, but A is growing like crazy. So anyway, so when the universe accelerates, the Hubble radius grows slower than the physical wavelength. And so you're in the opposite situation, that a physical wavelength starts off very tiny relative to the Hubble scale. So in the accelerating universe, you have this physical wavelength, and initially it's so small, relative to the Hubble scale, which is way out here, that it doesn't know about cosmology. It's like we in the solar system don't need to know about cosmology to describe the physics in the solar system. It's so long as to be irrelevant for us. Locally here, this guy lives in a little Minkowski, you zoom in enough around any patch of a manifold on scales much smaller than the curvature scale, and it looks like Minkowski space. So we start off with a little mode here at the beginning of the inflation epoch that basically thinks it's living in Minkowski space, couldn't care less about the expansion of the universe. But except that the expansion of the universe is making it grow relative to the Hubble scale. Eventually, and it's growing a lot faster. Okay, so during inflation, its physical wavelength is growing exponentially. The physical wavelength of the Hubble scale is not growing at all. It should not be going down again. So sometime not too long after this, because its growth is exponential in time, whereas this is just constant in time, it grows longer than the Hubble radius, and so that's the process. So what happens then? So again, there's some big transition where this guy behaves one way when it's inside the horizon, quote unquote inside the horizon. Yeah, this is in cosmology lingo. This statement about when you say a mode's wavelength is short relative to the horizon, you call it inside the horizon, and then you say, quote unquote, goes outside the horizon. And then later on, because later on the universe will start decelerating, and so at the end of inflation here, the universe will start decelerating, the Hubble radius will begin expanding again, while on the other hand, this guy will slow down. So at some point later in the expansion of the universe, these modes will cross back inside the Hubble radius, and you say quote unquote re-enters. This is called horizon re-entry. The combination of the fact that I can't write and I'm writing at the bottom of a board that I can't see. Anyway, this is horizon exit. It makes it seem. A person who didn't know better might think I had bad chalkboard skills. Okay, so what happens physically? So physically, this mode, when it's in the vacuum state, it's happy to just have its it's happy to just sit in the vacuum state. It has maybe some 0-point energy, 1/2 h bar omega. Let's imagine this is just a massless scalar field. Okay, so whatever its co-moving wavelength is at some time, you can define a corresponding, and it's common to define a corresponding co-moving wave number. So just like you normally take a wavelength and define a corresponding wave number to be 2 pi over that wavelength. You do that in cosmology, that's the co-moving wave number. And the co-moving wave vector is exactly the guy that's appearing here in this Fourier decomposition. When I say focus on a particular Fourier mode whose wavelength is constant in co-moving coordinates, its wave number is also constant, of course. Okay, so for a massless scalar field, its physical frequency, the actual frequency with which it oscillates, which would be the relevant thing for this h bar omega, is its wave number kc divided by a. So in other words, this is just like we would multiply by a to get from the co-moving wavelength to the physical wavelength. We have to divide by a to get from the co-moving wave number to the physical wave number. Okay, so in other words, this is just here. I'm just saying that the usual thing, that the wave number squared plus mass squared is the energy, or the frequency. And the only modification here is that if this is the co-moving wave number, I have to divide by a squared, and I'm looking at the case where the mass is equal to 0. Okay, so the frequency is equal to the wave number. So originally, when a is very small, omega is so big, omega is huge. You know, omega is the ground state energy of this mode, and it's also the spacing between that energy and the next higher energy level. You know, 3/2 h bar omega. Okay, so we just calculated that de Sitter space is actually just the fact that the universe is expanding means that it's as if you're in an oven with some finite temperature T, which is the expansion rate over 2 pi. But initially, when the wavelength is very small relative to the Hubble scale, that's equivalent to saying that this frequency is huge relative to the temperature of the oven. So the oven is not going to excite this mode up to its excited states with any significant probability, as long as this guy is very small. So the moment when you cross the horizon here, the moment when k physical becomes approximately equal to h, or in other words, 1 over the lambda physical becomes approximately equal to 1 over h, or in other words, the co-moving wavelength becomes equal to 1 over the co-moving Hubble radius. Remember this guy we talked so much about when we were discussing the homogeneous aspects of inflation. You know, that's exactly the moment when the temperature of the horizon is becoming comparable to omega. Okay, so you see this transition in the classical equations of motion for the mode functions. That's what we'll do when we calculate things in detail tomorrow. But physically, you know, this is an equivalent way to describe what's going on. De Sitter space is like an oven, and as the mode is getting stretched and stretched and stretched, omega is getting tinier and tinier and tinier. So the spacing between the energy states of this system is getting tinier and tinier and tinier until eventually the spacing gets so small that even though the oven might be really cold, it's hot enough to excite the field up into its excited states. Okay, so that's one point. So that's what a mode does. It basically stays in its vacuum state, and then right as it crosses the horizon, we say it gets excited, and perturbations get created. When we say quote-unquote perturbations get created, well, we'll see in detail what that means. But physically, that mode is getting excited out of the ground state by the de Sitter oven. And then another thing you'll hear about cosmology is that an observed fact about the universe is that if you measure the primordial spectrum of fluctuations, so we measure the cosmic microwave background. So this is an important point. Deserve this on board. So we looked at these plots of the cosmic microwave background where we were plotting. Remember, we were basically plotting CL, the average of the. We took this map of the cosmic microwave background. We measured the temperature at every point on the sky. We decomposed it in spherical harmonics. And then we averaged the we took the mean squared value of the spherical harmonics at a given L, all 2L plus 1 of them at a fixed L, and we plotted that as a function of L. And we get some curve with bumps and wiggles, and I showed that there was some theoretical curve plotted there, and then data points that beautifully agreed with the theoretical curve. So it's important to say that this bumpy thing is what we see several 100,000 years after the Big Bang. Okay, so let's say this is 300,000 years after the Big Bang. But when we're explaining it, when we're calculating the theoretical curve that fits it, the idea is that the initial spectrum of perturbations had no bumps. It's a perfect power law. So if you plot the sort of mean squared size of the perturbations in the early universe at the beginning of the radiation-dominated epoch, and you say, okay, we'll say in more detail what I mean by this later, but you say it's a power law in K. So as you change, basically if I pick a Fourier mode at random in the early universe and I ask what is its amplitude, well, first of all, the universe is isotropic, so it doesn't depend on the direction of the K vector corresponding to that Fourier mode. It only depends on the magnitude of the K mode, so it only depends on the wave number. And so then I ask, what if I pick a Fourier mode at random, how big should I expect its amplitude to have been at the beginning of the radiation-dominated epoch? What's the RMS value of that amplitude? The observational fact, the fact that this theoretical curve fits these bumps, is actually saying something simpler. It's saying the observational fact is that power spectrum is a perfect power law in K, and that furthermore that the spectral index is nearly 0. Turns out to be appears to be minus 0. More correctly, it appears to be minus 0.04 plus or minus about 0.01. So it's not quite 0. It statistically deviates from 0, but it's close to 0. So in other words, you pick a mode of any wavelength, choose its amplitude. It's basically the same. To first approximation, every mode, regardless of its wavelength, has the same RMS expected value for its amplitude. So we say that the perturbations in the early universe were quote-unquote scale invariant. And so here, that scale invariance, again, is ultimately the physical reason for it is that as I want my board back. So here, at this time, there was this mode, but then there was an even shorter wavelength mode. And then there was some longer wavelength mode that was still shorter than the horizon. So this long wavelength mode, let's say it crossed outside the horizon. Since it was longer, as everything stretched, it crossed the horizon first. And then this guy crossed the horizon a little bit later, and then this tiny guy crossed the horizon a little bit later, let's say right at the end of inflation. But the picture in inflation is that the universe was nearly de Sitter space. It wasn't just accelerating in the early universe. It was accelerating driven by a nearly constant vacuum energy. And so it was, that corresponds to saying that it had sort of a constant spatial curvature, 1 over h naught. In other words, in just perfect de Sitter space, the temperature here is a constant. It doesn't evolve in time. The idea is that inflation was like that. It was close enough to perfect de Sitter, to being driven by a pure cosmological constant. In other words, the vacuum energy density that would drive this is perfectly constant. The vacuum energy in inflation apparently was, if it was decaying very slowly, because in the limit that it's constant, the temperature of the oven just remains constant with time. And that has the effect that if that's the case, then we get an explanation for why every mode, as it crosses the horizon, gets excited the same amount. Every mode at the moment when it crosses the horizon is just like every other mode when it crosses the horizon. It's just some wavelength and it's been stretched, and then when it reaches this fixed physical size, the oven excites it, and then the next guy comes along, reaches the same physical size, gets excited by exactly the same process. Okay, ultimately, physically, this is the essence of why inflation predicts a scale invariant spectrum. Or you might, if you were more of a disbeliever in inflation, you would say, ultimately, this is why inflation has taken the energy density during the early universe to be nearly constant, so that it's approximately de Sitter with an approximately constant temperature. and in order to produce the scale invariant primordial perturbations that we observe. But maybe just one last comment here. So what are those perturbations? We had if the early universe had a perfect power law in K that was nearly flat, why is the thing we observe in the CMB bumpy like this? So again, that was the thing that came to Sakharov in a dream, and that we discussed briefly, I think, in 2 previous lectures. But the idea is that so now let's talk about. We'll start at the beginning of the radiation-dominated epoch and go forward until the moment when the CMB photons are released. So during that epoch, again, we're in the opposite situation, where the Hubble radius is not constant but is growing, and the wavelengths, the co-moving wavelengths, are not growing as fast, and so they're eventually coming inside the horizon. Okay, and here's the moment when the CMB was released. Okay, so what happens here? At the beginning of the radiation-dominated epoch, when these guys are all outside the horizon, they all have the same amplitude on average. They all have the same. They're all drawn from a distribution with the same variance to a first approximation. In other words, that was this whole business about k to the 0, wherever that went up there. And they stay, again, as long as it's outside the Hubble radius, the amplitude just the mode doesn't oscillate, it basically just stays fixed. At some point, the Hubble radius catches up to it, and suddenly the mode re-enters the horizon. Suddenly it's shorter than the Hubble length, and it's getting to just be a mode in Minkowski space. It's soon going to think it's just living in Minkowski space. Okay, so what does a density perturbation do once it's in Minkowski space? That depends on what sort of density perturbation it is. If it's just dark matter, if it's just pure density with no pressure, then the density perturbation wants to grow. The peak in the density has a little bit more gravity than the trough, and so it wants to pull matter onto itself out of the trough. And so the trough gets deeper, the density peak gets higher. So if you're pure matter with no pressure, like dark matter is, then once you enter the horizon, what you do is the amplitude of your perturbation just grows and grows and grows. So it comes inside here, and then it just grows and grows and grows until the CMB takes a snapshot of it. Okay, but the CMB does not take a snapshot of the dark matter directly. We haven't seen the dark matter directly. So there's another component in the universe, which is baryons, so protons and electrons, normal matter, I should say, protons and electrons, coupled to photons. See, up until this moment, the photons were so tightly, up until this moment, remember this is the moment when protons and electrons combined into neutral hydrogen atoms, but before that they were separate charged particles. Photons were so delighted they didn't know what to do with themselves, they were just knocking into electrons everywhere. So the electrons and the photons and the protons were all kind of a unified soup of, a unified plasma of material. And they had a hell of a lot of pressure because one of their main components were photons who have a lot of pressure. So instead of just growing here, they do something different. They might first grow a little bit, but they grow a little bit, and then they say, oh, wait a minute, my pressure has gotten, we overdid it. The pressure got too big for me over here. So the pressure is going to expel everything and drive the density back down again. But then it overdoes it again and oscillates. So this is just what a sound wave is. That you have two competing forces: pressure wanting to iron out the oscillations, gravity wanting to enhance them, and they oscillate as they compete with one another. And the fact that beneath them there is this big growing dark matter perturbation just has an overall effect of enhancing the effect of gravity. The dark matter is not just gravitating on itself, it's also pulling on this gas of photons and electrons. and increasing the strength with which it wants to get pulled into the potential wells. But so anyway, it's this oscillation that happens after you enter the horizon. The fact that on certain wavelengths, at the moment when the CMB takes its snapshot, at certain wavelengths happen to be at maxima of their oscillations, whereas other wavelengths happen to be at nodes, and other wavelengths happen to be at anti-maxima. That's what's ultimately responsible for the fact that as a function of angular scale on the sky, that snapshot has oscillations in it. So the key point is that, when people show this plot, it looks like super impressive. Some crazy wiggly plot, and then they say inflation predicted this curve, and then the data lies perfectly on it. I mean, it's actually quite a misleading statement. The thing that is super impressive is that the perfect, so really all you need, the ingredient that inflation needs to put in there is a constant, perfect power law, scale invariant spectrum of perturbations at early times. It's a rather simple featureless thing. So if they came with the data and they showed you, if the CMB experimentalists could somehow look directly into the early universe for what inflation did, and they came and they showed you a plot that looked like, just like data points, and they were like, look, it's all perfectly consistent with a horizontal line. It's like case closed. Inflation is right? I mean, you would be much less impressed by it. I think you should be much less impressed by it. So, but that is really the exact situation. What you should be impressed by about the CMB, the thing that the CMB clinches without, there's no more wiggle room, is that, we understand the physics of the early universe during the radiation-dominated and matter-dominated epochs between, between the times when all of these modes that you see re-entered the horizon and then the CMB snapshot was taken. You give it a primordial spectrum of perturbations that is scale invariant, and then the known laws of physics, together with the standard Big Bang predictions for what amount of, together with the standard lambda CDM predictions for how much dark matter there is, and how much photons and how much electrons. All that evolution that took place between a couple of minutes after the Big Bang, when Big Bang nucleosynthesis happened, and a few 100,000 years, there's very little wiggle room. All you need to provide is a scale invariant spectrum of perturbations at early times. And it has to be Gaussian in statistics and adiabatic. So inflation does get several things right. I don't mean that you shouldn't be very impressed by it. It's the most successful, observationally successful predictive theory of the early universe that we have. It's made the most successful predictions. It predicted the near scale invariance, near power law spectrum, that it should be Gaussian, and that it should be quote unquote adiabatic, which is something we haven't discussed yet. But it's not as impressive as this wiggly curve business. That's a completely separate thing that increasingly is not separated in talks. Anyway, so I'll end there. So tomorrow we just want to actually do the. So I will sort of sketch enough of the calculation that's done on the homework. You calculate the spectrum yourselves.